Computer Science 410, Computer Architecture, Processor Structure and Function Part 2. This lecture covers chapters 14.4 to 14.6 of the 10th edition of the textbook. Here I'll be focusing on pipelining, which is section 14.4, as opposed to the details of the x86 and ARM architectures. To be sure, I'll cover those two things, but I really want to focus on pipelining. So we can begin with the little layout of pipelining, and basically it's an organizational approach to performance enhancement as opposed to relying on faster circuitry. Pipelining works in a manner that's similar to an assembly line. We work on many different things simultaneously, and this is possible due to instructions having a number of different stages. Let's begin by looking at an example two-stage instruction pipeline. So, as a simple approach, consider subdividing the instruction processing into two stages. 1, fetch, and 2, execute. There are times during the execution of an instruction when main memory is not being accessed. We could use this time to fetch the next instruction in parallel with the execution of the first. This is figure 14.9 and depicts this approach. The pipeline has two independent stages. The first stage, fetch, fetches an instruction and buffers it. When the second stage is free, the first stage passes its buffered instruction to the second stage. While the second stage is executing this instruction, the first stage takes advantage of any unused memory cycles to fetch and buffer the next instruction. This is called instruction prefetch or fetch overlap. Note that this approach, which involves instruction buffering, requires more registers. Part B shows this pipeline in more detail, and we don't actually get double performance from this for a couple reasons. One, the execution time is a bit longer to perform the fetch, and two, jump instructions can throw a monkey wrench into the works. We'll talk about that a little bit later, but we can perform some guessing to make this performance a little bit better. So we can actually expand this to additional stages to get further speed up. So one of these stages is fetch instruction, which reads the next expected instruction into a buffer. Decode instruction, determine the opcode and operand specifiers. Calculate the operands, calculate the address of each of the operands that we're going to perform the operation on. This could involve displacement, indirect, direct, or other forms of address calculation that we saw in the previous chapters. Fetch operands. Fetch each operand from memory. Operands in the registers need not be fetched. It's because they're already in the registers, of course. Execute instructions. Perform the indicated operation. Store the result, if any, in the specified destination operand location. And write operand, which is storing the result in memory. With this decomposition, the various stages will be a more or less equally long duration. Let's take a look at the way that our six-stage pipeline could work. So, for the sake of illustration, let's assume these things are all of equal duration. It's not necessarily true, but let's use that assumption. This figure, which is 14.10 in the text, shows that a six-stage pipeline can reduce the execution time for 9 instructions from 54 time units down to 14 time units. So that goes from 54 down to 14. The diagram assumes that each instruction goes through all 6 stages of the pipeline. Now, that's not always the case. For example, load doesn't need the write out stage. However, to simplify the pipeline hardware, the timing is set up to assume that each instruction requires all 6 of the stages. Also, the diagram assumes that all the stages can be performed in parallel. In particular, it assumes that there's no memory conflicts, which isn't always going to be the case. Several other factors serve to limit the performance enhancements. The 6 stages were not of equal duration. There would be some waiting involved at various pipeline stages, as discussed with that 2-stage pipeline that we talked about on the last slide. Another difficulty is the conditional branch instruction, which can invalidate several instruction fetches. And a similarly unpredictable event is an interrupt. Let's see what the effect of a conditional branch might be on the way this 6-stage pipeline performs. And here it is with a jump in there. And this illustrates the effect of a conditional branch using the same program. Now, assume instruction 3 is a conditional branch to instruction 15. Until the instruction is executed, there's no way of knowing what instruction will come next. The pipeline in this example simply loads the next instruction in the sequence, that is instruction 4, and begins proceeding on processing instruction 4. On the last slide, the branch is not taken and we get the full performance benefit of the enhancement. In this one, the branch is taken, and this is not determined until the end of time unit 7. At this point, the pipeline must be cleared of instructions that are not useful, and we can proceed to instruction 15, which takes place during time unit 8. No instructions are completed during units 9 through 12. This is a performance penalty incurred because we couldn't anticipate the branch. Now it comes to question, it might seem like more stages gives us a faster execution rate, and that's true up to a point. But three factors prevent or limit this. One is there's an overhead moving data from buffer to buffer and then performing various preparation and delivery functions. You also need more control logic to optimize the use of the pipeline, and there's also a latching delay, which is the time it takes for pipeline buffers to operate, and that of course adds to the instruction cycle time. So depicted in this slide is the flow chart for the 6-stage pipeline. In regard to conflicts, calculate operand stage may depend on the contents of a register that could be altered by a previous instruction, so that could create a conflict. Other register and memory conflicts can also occur, and the system must contain logic to account for this type of conflict. So pipelining is really powerful, but it requires careful design in order to get optimal results and to avoid those conflicts, and we'll take a look at some of the ways to do that a little later on in the lecture. So there are some formulae for for pipeline performance, and one of these is the cycle time of an instruction pipeline, and that's known as tau, and that's basically the time you need to advance a set of instructions one stage through the pipeline. That's the max of the time delay for the circuitry, plus d, which is the time delay of the latch needed to advance signals and data from one stage to the next. And if you take a closer look at pages 504 to 506, you can also find some equations for the total time required for an instruction to go through k stages and to calculate the speed up for an instruction pipeline. So in looking at that speed up, these two graphs show the potential speed up factor. The first one shows it as a function of the number of instructions that are executed without a branch, and that's asymptotic to the speed up factor. 14.14b, which is the one at the bottom, shows the speed up factor as a function of the number of stages in the instruction pipeline. In this case, the speed up factor approaches the number of instructions that can be fed into the pipeline without branches. Thus, the larger number of pipeline stages, the greater the potential for speed up. However, as a practical matter, the potential gains are countered by increase in costs, delays between the stages, and the fact that branches will be encountered that require full flushing of the pipeline. So another thing we need to be aware of are hazards. And a pipeline hazard is something that occurs when the pipeline or some portion of it needs to stall or take a pause because conditions don't permit continued execution. There are three types of hazards that we'll talk about on the coming slides. These are resource, data, and control. And if you do like hazards, though, you can enjoy the Hazards of Love by the Decemberists, which is a pretty good album. So let's start by talking about resource hazards. And a resource hazard occurs when two instructions that are already in the pipeline need the same resource. It results in instructions that must be executed in serial rather than in parallel. So let's consider a simple example. Assume that a simple 5-stage pipeline, which each stage takes one cycle. The top shows the ideal case in which a new instruction enters the pipeline each clock cycle. Now, assume that main memory has a single port and all instruction fetches and data reads and writes must be performed one at a time. And we can also ignore the cache in this case. In this case, an operand read or write from memory can be performed in parallel with an instruction fetch, and that's illustrated in the figure at the bottom, which assumes that the source of the operand is in memory rather than in a register. And that's where you see the idle come in. So therefore, the fetch instruction stage of the pipeline needs to idle for one cycle before bringing the instruction fetch for instruction number 3. The figure assumes that all other operands are in the registers. Another example of a resource conflict is a situation in which multiple instructions are ready to enter the execute instruction phase, but there's only a single arithmetic logic unit. One solution to resource hazards is to increase the number of available resources, such as having multiple ports in memory and multiple arithmetic logic units. Reservation tables are another solution that are discussed in Appendix N if you're interested in looking at it. Let's turn our attention to data hazards. And a data hazard occurs when there's a conflict in the access of an operand location. There are three types. One is read after write, or true dependency. So here an instruction modifies a register or memory location. The next instruction reads data in the memory or the register location. And the hazard occurs if the read takes place before the write operation is complete, because we don't have the update instruction. Right after read, an instruction reads a register or memory location. Next instruction writes to that location. The hazard occurs if the write operation completes before the read takes place. And then right after write, or output dependency, two instructions both write to the same location. The hazard occurs if the write operations take place in the reverse order of the intended sequence. So another type of hazard are control hazards. These are also known as branch hazards. These occur when the pipeline makes the wrong decision on branch prediction. Brings instructions into the pipeline that needs to be subsequently discarded, and there are different ways of dealing with this. One is multiple streams, another is prefetch branch target, a third is loop buffer, fourth is branch prediction, which has a number of sub options to it as well, and then delayed branch. We'll look at multiple streams first. So this is a solution to the problem of dealing with branches from the control hazards portion, and this is called multiple streams. And a simple pipeline suffers a penalty for branch instructions because it must choose one of the two instructions to fetch next, and there's a possibility that it makes the wrong choice. A brute force approach is to just replicate the initial portions of the pipeline and allow the pipeline to fetch both instructions, making use of two streams. There are a couple of problems with this. With multiple pipelines, there are contention delays for access to the registers and to the memories, and additional branch instructions may either enter the pipeline before the original branch decision is resolved, and each instruction needs an additional stream. Despite these drawbacks, this strategy can improve performance, and this was implemented on the IBM 370 and the IBM 3033. Prefetch branch target is another approach. When a conditional branch is recognized, the target of the branch gets prefetched in addition to the instruction following the branch. The target is then saved until the branch instruction is executed. If it's taken, the target has already been prefetched. That one's pretty self-explanatory. Let's look at the loop buffer approach. And the loop buffer approach makes use of a small, very high-speed memory maintained by the instruction fetch stage of the pipeline and containing the n most recently fetched instructions in sequence. This is beneficial because instructions fetched in sequence will be available without the usual memory access time. If a branch occurs to target just a few locations ahead of the branch instruction, we'll already have that target in the buffer. This strategy works particularly well when you're dealing with loops, because that's how loops are structured, and that's why it's known as loop buffer. It's similar in principle to a cache dedicated to instructions, but with a couple differences here. Loop buffer only retains instructions in the sequence and is much smaller in size than a cache, and it's also lower in cost. Another approach is branch prediction. There are various techniques that have been used to predict whether a branch will be taken. Now, the first three of these are static. They don't depend on execution history up until the time of the conditional branch instruction. One is predict never taken. The second is predict that you're always going to take it. And then predict by opcode. The first two approaches are the simplest. They either always assume that you're going to take it, or you're always not going to take it. The predict never taken approach is the most popular of these different models. Studies analyzing programs' behavior have shown that conditional branches are taken more than 50% of the time. And so if the cost of prefetching from either path is the same, then you always want to prefetch from the branch target address, which will give you better performance because it's more than 50% of the time. However, in a page machine, prefetching the branch target is more likely to cause a page fault than prefetching the next instruction, so you need to account for that as well. An avoidance mechanism can be implemented to employ this penalty. The final static approach, which is predicted by opcode, assumes that the branch will be taken for certain branch instructions, branch opcodes, and not for others. There have been reports of success of greater than 75% with this strategy. And then a couple dynamic approaches are the taken, not taken switch and branch history table. And these basically attempt to improve the accuracy of prediction by recording the history of conditional branch instructions in the program. For example, one or more bits can be associated with each conditional branch instruction taken that reflect the most recent history of the instructions. These are referred to as the taken, not taken switch and direct the processor to make a particular decision the next time the instruction is encountered. Typically, these history bits are not associated with the instruction in main memory. Rather, they're kept in a temporary high-speed storage. One possibility is to associate these bits with any conditional branch instruction that is in a cache. When the instruction is replaced in the cache, its history is lost. Another possibility is to maintain a small table for recently executed branch instructions with one or more history bits in each entry. The processor could access the table associatively like a cache or by using low-order bits of the branch's instruction address. So that's pipelining. Let's take a look at the x86 processor family. And as you know, this one has evolved quite a bit over the years. It has a register organization, which is important for talking about how the processor is designed. And let's look at the register organization for integer processing. General, there are 8 32-bit general registers. These are used for all types of instructions. They can also hold operands for address calculations. And in addition, some of these registers also serve special purposes. In 64-bit mode, there are 16 64-bit general purpose registers. Segment, the 6 16-bit segment registers contain segment selectors which index into segment tables. Flags, there's the Eflags register that contains certain codes. We're going to talk about that. And in 64-bit mode, the register is extended to 64 bits and is referred to as R flags. And then the instruction pointer contains the address of the current instruction. There are also registers devoted to 64-bit integers, and you can find them on page 517 of the text. Let's take a look at the floating point registers. There are a number of registers that are specifically devoted to floating point units. Numeric, each register holds an extended 80-bit floating point number. There are 8 registers that function as a stack with push and pop operations available in the instruction set. Control contains bits that control the operation of the floating point unit, including the type of rounding control, single, double, or extended precision, and bits to enable or disable various exception conditions. Status, the 16-bit status register contains bits that reflect the current state of the floating point unit, including a 3-bit pointer to the top of the stack, condition codes reporting the outcome of the last operation, and exception flags. And then tag words, 16-bit register contains a 2-bit tag for each floating point numeric register. And there are different possible values. But let's turn our attention to the Eflags register, and this indicates the condition of the processor and helps control its operations. It has 6 condition codes, carry, parity, auxiliary, zero, sign, and overflow, which report the results of an integer operation. And there are bits in the register that can be referred to as control bits. Trap flag, when set, causes an interrupt after the execution of each instruction. This is used for debugging. Interrupt enable flag, when set, the processor will recognize external interrupts. Direction flag determines whether string processing instructions increment or decrement the 16-bit half registers. I/O privilege flag, when set, causes the processor to generate an exception on all access to I/O devices during the protected mode operation. Resume flag allows the programmer to disable debug exceptions so that the instruction can be restarted after a debug exception without immediately causing another one. Alignment check activates if a word or double word is addressed or a non-word on a non-word or non-double word boundary. An identification flag can be set and cleared. The processor supports processor ID instruction. This particular instruction provides information about the vendor, family, and model of the processor. And there are also 4 control registers, which have a heck of a lot of flags that you can see there in the lower right, and there are also registers devoted to multimedia. If you want to see the details of all these different flags, they're on pages 320 to 321 of the text. Both interrupts and exceptions can suspend the execution of a program. There are 2 sources of interrupts that depend on which pen receives the interrupt. Maskable and non-maskable are the 2 different types of interrupts. And 2 sources of exceptions. One is processor detected exceptions that result when the processor encounters an error while attempting to execute a particular instruction, and then programmed exceptions. These are instructions that generate an exception, for example, the N2 command. Now let's look at the ARM processor. And ARM is primarily a RISC, which is a reduced instruction set computer system with the following attributes. It has a moderate array of uniform registers, that is not too few and not too many. They talk about what not too few and not too many mean in section 14.6 of the book. A load store model of data processing, which operations only perform on operands in the registers, and you don't do loads and stores directly into memory. Uniform fixed length instruction, 32 bits for the standard set and 16 bits for the thumb instruction set that we talked about last chapter. Separate arithmetic logic unit and shifter units. A small number of addressing modes with all load store addresses determined from registers and instruction fields. Auto increment and auto decrement addressing modes are used to improve the operation of program loops, and conditional execution of instructions minimizes the need for conditional branch instructions, thereby improving the pipeline efficiency because pipeline flushing is reduced. So there are a number of different modes, and there are 7 execution modes. Most of the time, and for most application programs, they're executing in user mode. The remaining 6 execution modes are referred to as privilege modes. These are used to run the system software. There are 2 principal advantages of defining so many different privilege modes. One is the OS can tailor the use of the system software to a variety of circumstances, and certain registers are dedicated for use for each of the privilege modes, allowing swifter changes in context. There are also exception modes in ARM. The exception modes have full access to system resources and can change modes freely. 5 of these modes are known as exception modes. They are entered when specific exceptions occur. Each of these modes has some dedicated registers that substitute for some of the user mode registers, which are used to avoid corrupting the user mode state information when the exception occurs. And last but not least, registers, and just like the x86, there are a lot of registers. The ARM processor has a total of 37 32-bit registers that are classified as follows. There are 31 registers referred to in the ARM manual as general purpose registers. In fact, some of these, such as program counters, have special purposes, but they're still referred to as general purpose. And there are 6 program status registers. They're arranged in partially overlapping banks, with the current processor mode determining which one of the banks is available. At any time, 16 numbered registers and 1 or 2 program status registers are visible, for a total of 17 or 18 different visible registers. And that's what's depicted in this figure. Registers R0 through R7 and register 15, which is the program counter, and the current program status counter, are visible in and are shared by all different modes. Except the fast interrupt. R8 through R12 are shared by all modes except fast interrupt, which has its own dedicated registers R8 through R12. All the exception modes have their own versions of registers R13 through R16, and all exception modes have a dedicated saved program status register, SPSR. And that's the end of this particular chapter. And that's all for now. Thanks for listening.